In this section of notes, we're going to be switching over to a new type of data. So in previous lessons, we looked at categorical data and all of the different ways we could display it. So we used pie charts, we did bar graphs, we did segmented bar charts, we did mosaic plots. Now we're switching over to quantitative data and the types of displays that we can use for that. So the first type of display is a dot plot. And you can see on the dot plot here, it's basically just a number line. Again, you want to have a label, so you want to know what the dots represent. And the scaling should be appropriate. So again, the space between 0 and 2 should be the same as the space between 2 and 4. And then each dot represents one outcome. So in this dot plot, there's a dot at 0. So that represents a game where there were 0 goals scored. And then there's 4 dots at 1, so that would represent 4 different games where there was 1 goal scored. So again, here's a dot plot. And this would be analogous to this same set of data that's here. Now, once we have our data displayed, a very common question that you'll see is that you'll be asked to describe the distribution of the data. And when you give the distribution, you're going to give a 4-part answer. You're going to address the shape, the center, the spread, and the outliers. And sometimes we use the acronym SOX, shape, outliers, center, spread, to help us remember that. You might also sometimes see spread relabeled as variability, and that's just another word for that. So variability is another word for spread. Now, when we go to address shape, we want to look at whether or not the distribution is symmetric or skewed. So symmetric, you probably remember that. That's like if you could fold it in half, it would look the same on the left and the right. And then there's also skewed to the left and skewed to the right, or you can say right skewed or left skewed. That just means that there's like a tail on the data. So there's a lot of data clustered on one side, and then there's fewer data clustered on the other. And then whichever side the tail is on is the side of the skew. So here are 3 distributions. The first one is roughly symmetric. It's not perfect, so we're going to add an ly word to kind of soften that claim, and we'll say it's roughly symmetric. Whereas the second one here is an example of something that's skewed to the left. So you have fewer data points on the left-hand side of that number line, and you've got more on the other side. And then the last one is skewed to the right. Now, another common question, instead of just being given one distribution and being asked to describe its shape, center, variability, and outliers, sometimes you'll be given 2 distributions and then you'll be asked to compare them. When you compare, you do the same 4 things, except for you need to make sure that you use a comparative word, like higher, lower, more, less, or similar. So if they're not different, you can say that they're similar. So you can say they have a similar shape, or you can say the South Africa group has a more skewed distribution than the UK group. So you say one is more skewed, one is less skewed, one is more symmetric, one is less symmetric. Something along those lines. Another option for displaying quantitative data, in addition to a dot plot, we can also use a stem and leaf plot. Now you might remember these from middle school or earlier. So when you go to make a stem plot, you're going to somehow break up the numbers. So like if your numbers are, they go out to like 1 decimal point. So your numbers are like 1.5, 2.4, 3.7. You'd probably make the decimal point be the leaf and the whole number part be the stem. But if your numbers are like values that are all 2-digit numbers, like 21, 32, 15, then you'd have like the tens digit be the stem and the ones digit be the leaf, and then you'll reorder them and it'll start to look something like this. So here's our list of numbers, and there's 20 of them here, and we asked some female students, we said, how many pairs of shoes do you have? And we want to complete a stem plot. So if we kind of gaze through all of these numbers, we can see some values that are relatively small, like 13, and we can see some that get pretty big, like 51. So our numbers are all 2 digits. So we're going to have the tens place be the stems, and then we're going to have all of the ones places be the leaves. After we've done that, we'll reorder the leaves from smallest to largest, and then we add a key. So we don't know just by looking at it, does the 1/3 mean 1.3, or does it mean 13, or what does it mean? So we do have to add a key so we know what that means. Now there are a couple variabilities on different types of stem plats. We can do split stem plats if you have all of the data clustered around one area and it's hard to see how it's distributed. Or you can also do back-to-back stem plots if you have more than one subgroup. So here we have males and females. We can split the stems. So 0, 0, we've got 2 zeros, we've got 2 ones, we've got 2 twos. So the first number would have the lower half of the data, so ones digits between 0 and 4. And then the second repeated stem would have the upper half of the data, so ones digits between 5 and 9. And we could look at males and females. We can put them back to back like this. So we could have the males on the right and the females on the left. So that is an example of the back-to-back stem plot. And you can use that to compare 2 populations. And of course, we still want to remember our key, whether it's a split stem plot or a back-to-back stem plot or just a regular stem plot. Next up, we have histograms. So this is another way to display quantitative data, besides dot plots and stem plots that we've already seen. So to make a histogram, we're going to take all of our numbers from smallest to largest, and we're going to somehow split them up into equal width. So like, are you going to split them into groups of 5 or groups of 10? And then we're going to count how many are in each of those subcategories, or sometimes we call them bins. And then it's almost like a bar graph, except for because this data is quantitative and usually sometimes it could be continuous, then those bars end up touching. So let's say we have some data here. So this data represents looking at each of the 50 states. So each state has a data value associated with it, and the percentage of the people in that state that were born outside of the United States. So here we can see there would be 20 states that had between 0 and 5% of the people born outside of the United States. And there's only one state that has between 25% and 30% of people born outside of the United States. Each of those counts turns into a bar. Notice they're touching in a histogram. So in a histogram, since they're going from 0 to 5 and then 5 to 10, the 5 is the same number, so the bars touch. Also notice that the 5 is strictly less than 5 for the 0 to 5, and then the 5 to 10, the 5 is included. So if you had a state that had exactly 5% of people born outside of the United States, it would go in the next up bin. It would go in the 5 to 10 bin rather than the 0 to 5 bin. Some things you want to be on the lookout for, some common mistakes for histograms. So again, be very careful here. A common mistake is to confuse a histogram and a bar graph. Remember, bar graphs have the spaces between, and that's for categorical data. Histograms have no spaces between, and that's for quantitative data. Be careful about the numbers that show up in the tables. They're not your data. They are how high your bar graph would go. Make sure when you make a histogram, your y-axis is allowed to be either counts or percentages, but if you need to compare 2 groups, then you need to have percentages. And be careful about interpreting the graph. Sometimes a graph is nice looking, but it's not particularly useful.